Hi everyone, my name is Andy Baker. I'm a lecturer in the School of Biological, Earth and Environmental Sciences in UNSW, and I'm recording these lectures from home in the pandemic. So this is coming to you from the central coast of New South Wales, and I hope it finds you safe and well. I've divided my lectures into smaller slide sets so that you can watch them back in convenient chunks. And I'm going to start off with this first set of slides that talks about something called LumpedParameter Modelling, and I'm going to explain what that is in the context of groundwater flow modelling in general. So why might we be interested in modelling groundwater flow? We can make measurements of groundwater. You can go to a bore or a well, and you can dip the water level, and you can measure that over time, and you can see how water levels are going up and down over time, and make some causal relationships between the water level changes and different environmental processes that are taking place. So that's okay for the modern day, or for the historical period where we have analogues between the two. But what about in the past or into the future? This is when groundwater modelling comes into its own. And I've given a few sets of examples here on this slide. Maybe we want to generate or make a groundwater flow model so that we can understand the future impact of groundwater abstraction, maybe by mining or agriculture, or maybe there's going to be a government policy that increases the damming of river systems, and we're interested to find out how the dam might affect river groundwater interactions. Maybe we have some climate change scenarios that say that it's going to be warmer and there's going to be more evapotranspiration, or it's going to be drier and less recharge, and we want to make a model to see how that might impact groundwater levels and groundwater flow. And maybe you're interested in contamination, so maybe there's a landfill and a landfill leachate plume, and you want to know how that's going to move into the future. And the picture below is of the UNSW Wellington Research Station, and if you really zoom into that slide after the lecture, you can start counting the blue bores, and there's about 40 bores on this site, and it's adjacent to the Macquarie River. And this is normally where we take students to actually investigate groundwater levels, and we can compare the groundwater levels in the bores to processes such as dam releases on the Macquarie River, and we can look at water quality in those bores and related to things like the local town landfill leachate plume, which is coming through the bore field just to the left of that shot and out of the field of view. So that picture's from Wellington in the central west of New South Wales. And if it wasn't a pandemic era, probably we'll be taking student groups there and actually getting you to make first-hand measurements of groundwater levels. So you already have a lot of detail on the course about groundwater modelling. I think it's lecture 5 of the course notes from Martin Anderson. So I'll refer you back to the very detailed notes you have from Martin, which explains how you might go about coding up a typical mathematical groundwater flow model. This is just a summary slide to remind you of some of the basic principles in those notes from lecture 5. And the reason why I'm doing this is that LumpedParameter modelling is slightly different, hence the recap here. So a typical mathematical model that you've learned about earlier in the course will describe the physical processes and the boundaries of a groundwater system using one or more governing equations, and you've been presented with those in your course notes. And typically a numerical model will then divide space, maybe space and time, into discrete chunks of space or time. And then the equations will be applied to those discrete pieces and to the boundaries. And the features of the governing equations and the boundary conditions are therefore specified over space and time, and you can generate a model that you can then use to, for example, predict or forecast future changes in groundwater level, providing you've got your model correctly conceptualized. So if you consider the mathematical models that you've learned about already, then they require the principle of mass conservation. That is, for the elementary control volume of your model, the change of the storage of the water or solute mass within the volume equals the difference between the mass inflow and outflow. So you have to balance the water. And the question therefore is, can you actually do this? So based on the equations and the empirical laws that you know, can you actually balance the water in your model? And finite difference and finite element models, you see some examples at the bottom of this slide for different meshes and grids. They have to obey the principle of mass conservation. LumpedParameter models, the models I'm going to talk about, don't have to do that. And that's important sometimes when you don't know where the water's moving. And this goes back to my expertise in karst hydrology. And again, karst is a type of limestone which has become soluble. It's full of caves and conduits, and the water can move very rapidly through these cave and conduit systems, but we don't know where they are, and the water can move very rapidly through these systems, and we very regularly cannot obey the principle of mass conservation because we don't know where the water is going. So we use a simpler type of model, and a lumped parameter does what the name suggests. It lumps all the equations into a single box or parameter or bucket and treats them as one, and doesn't try to model the fine detail at a finer resolution because we just don't know what it is. And it's a very appropriate modeling framework for systems where you have very limited control or understanding or knowledge of your groundwater systems. And the example on the right hand corner is an example of a conceptualization of a LumpedParameter model. I will spend a few seconds just to go through the different boxes because you'll see a few more of these later on in these lectures, and that'll be useful. So in the bottom right hand corner we have a LumpedParameter model, and we have a bucket at the top where there is precipitation or P going into it, so we need that data to run the model, and we have evaporation or evapotranspiration, which is E, leaving the model. And that bucket is called S/E, which is soil, and something called epikarst, which is the near surface geology. And you can see that water can leave that bucket by two different ways: from the bottom of the bucket, so draining out the bottom, leaking out, and also overflowing if that soil gets too full of water, and it goes down to the next water box or bucket. And that's labeled VZ. That's the Vado zone. So the Vado zone is the zone of Earth's surface which is unsaturated, and it can include the soil and includes the geology down to the water table. And you can see there that bucket can then drain two different ways into a groundwater system. One is called S, one is called F. That's the bottom two buckets. This is the groundwater system which is slow, and the groundwater system which is fast. And then they have outputs to the springs. So this LumpedParameter model is parameterized and run, and the only data you need to run it is precipitation, evaporation or evapotranspiration, and some hydrographs from the two springs. And then you optimize the model so that the model produces the same shape of the hydrographs, the spring outlets, compared to the observed data. And that's all the evidence you need to have a model, and hopefully then you understand something about the size of the soil water store, the size of the Vado zone water store, and the relative importance of the slow and the fast water movement components of the groundwater system. So at this point, I think it's useful to actually show you a section through a karst hydrological system, so you can see how complex it is. So the picture on this slide is from the 9th longest cave system in the world. It's 176 kilometers, and that's the known passage. And you can see on this system there's river systems on the surface to the left and the right of the image, flowing from the bottom to the top. And you see these cave systems exist where the water has moved underground, dissolved the limestone, and formed basically a series of underground drainage systems. And it's complex. You can see there's some preferred orientation, but if you didn't know where the caves were, you couldn't really predict it. And it's these caves and conduits that are going to be dominating the groundwater flow in these systems. We can't use a finite element or a finite difference model over this system because we don't know where the conduits are for a large part of it. The LumpedParameter modelling approach is the only approach we could use. And so, as I say here, it's a parsimonious modelling option for complex or data or geology. Parsimonious means simplest and best. So to summarise, LumpedParameter modelling is based on a conceptual modelling approach, something also called a grey box model, where data availability is low. And the hydrological processes are aggregated together into the key responses and are used as predictive models or to quantify groundwater processes, in this case, karst hydrological processes. One of the limitations of these approaches is that in these LumpedParameter or grey box models, you can over-parameterize them. That is, given this example on the right-hand side, you can put in too many stores and buckets. And if you over-parameterize your model, then your model becomes more uncertain in your output. So the best LumpedParameter models are the most parsimonious. They are the simplest model structures that can give an acceptable result. So that explains the basics of LumpedParameter modelling. Before we come back to some actual models and how to use them, I need to go and spend some time explaining something about karst hydrogeology. That's in the next set of slides.